Section 10.2, Rational Exponents. Alright, so in the previous section we looked at negative exponents and how to deal with those, and in this section we're going to look at how to deal with rational exponents, and specifically what we mean by that is exponents that are fractions. So let's start off looking at an example, trying to figure out what is 49 raised to the 1/2 power. So we have that fraction as our exponent, we're trying to sort out what that means. So let's go ahead and play around with that a little bit. Let's take that 49 to the 1/2, and to try and figure out what that means, I'm going to take that and square it and see what I get. So in chapter 7 we learned that if you have a power raised to a power you multiply the exponents, and that's still true here. So this would be 49 to the 1/2 times 2, and the 2's would cancel there and we just get half of 2, so 49 to the first, or just 49. So whatever 49 to the 1/2 is, when you square it you get 49. So then we could start thinking, well, what number do we know that if we square it we get 49? And the answer to that is 7. So it seems like 49 to the 1/2 might be 7, because if that was true, 7 squared would equal 49. Another thing that we could look at here is that the 1/2 is canceling with the exponent of 2, or the squaring process, which means those are opposite or inverses of each other. And if two functions are opposites, then that can give us a clue into what kind of function they are as well, because we should already know what the opposite of squaring is. From chapter 9 we should know that that is a square root. So a rational exponent like 1/2 is actually just another way of taking a root, and the denominator tells us what kind of root that is. So my claim here is that 49 to the 1/2 means the same thing as taking the square root of 49, and the square root of 49 is 7. And just thinking about, does that make sense? What if I plug the 7 in here for 49 to the 1/2 and I squared it, I would get 49. So that's going to be the way we end up thinking about these rational exponents, is that the denominator tells us what kind of root to take. So similar to that, if you see 27 raised to the 1/3, then because the denominator is a 3 rather than a 2, we're going to take that to mean that it is a cube root rather than a square root. So 27 to the 1/3, I'm going to say that's equal to the cube root of 27. And just like a square root says what times itself gives me 7, this says what times itself 3 times gives me 27. So here we would say 7 squared is 49, so 7 is the square root of 49. Here we would say, what is it that if I raised it to the 3rd power would give me 27? And the answer should be 3. So I'm going to go ahead and box that as our answer, but I want to check it for you as well. If I take 3 and I raise it to the 3rd power, I get 27. So that is the indication that that is the cube root of 27. But then, does 27 to the 1/3 really mean that? So my claim is 27 to the 1/3 is the same as 3. Let's test that by taking 27 to the 1/3, raising it to the 3, and if that's really 3, then when I raise it to the 3rd I should get 27. So if I raise it to the 3rd, I have power to a power, so I'd multiply 1/3 times the 3. The 3's would cancel, I'd just get 27 to the 1st, or 27. So it does look like that's checking out. It might still be a little confusing at the beginning, but we'll keep practicing this to get used to it. But here's a summary of what I'm claiming here. If you have b raised to the 1/n, where n is some counting number and not 1, then if n is odd, then b to the 1/n is the number whose nth power is b, and that's called the nth root of b. So again, our example there is if we have a 1/3, that is the 3rd root or cube root of 27. And then if n is even, then you need the base to be positive, and then you would still say it's the nth root of b. Numbers that are, when you take an even root, you get both a positive and a negative root are possible, but when we write it this way, we're going to want that to be the principal root or positive root, like we talked about with square roots in chapter 9. And then finally, if n is even and b is negative, then you don't have a real number. So the kind of shorthand summary of that whole box comes from this line right here that says, if you see b to the 1/n, you can rewrite that as the nth root of b, and that's true for all these different cases. They would still work out. So let's go ahead and think about that with some more examples. 9 to the 3 halves doesn't quite fit this mold because of the 3. So what you can do with something like that is make it 9 to the 1 half and peel the 3 from the numerator off as its own power. Now remember, a power to a power you multiply, and 1 half times 3 is 3 halves. So these really are equivalent, but this gives us a way to peel off that numerator so we're looking at something that's 1 over that fits this form. So I would say that 9 to the 1 half is the same as the square root of 9, because that denominator tells me what kind of root to take, so a square root, and then I still have that 3 out there. And after that I would just work it through in steps. The square root of 9 is 3, and then we still have the exponent of 3, and 3 to the third is 27. Let's look at another one. Same idea, 27 to the 4 thirds. I'm going to say that's 27 to the 1/3 raised to the 4th power. So separating the numerator and denominator off. Again, power to a power, you'd multiply these and it would be back to that 4 thirds again. But I want to look at the denominator part with a 1 over, so I can think of it as an nth root according to this part up here. So I would rewrite this as the cube root of 27, and that power of 4 I would just leave on the outside, and then I'm just going to work it through and say, alright, what is the cube root of 27? That's 3. And the way I'm thinking about that is what raised to the third gives me 27, and 3 raised to the third would be 27. And then I still have that 4 from the outside, so I work out 3 to the 4th, and you can do that on a calculator or scratch work. But 3 raised to the 4th power does give 81. So that is our answer to that one. And let's go ahead and look at one more of these with the rational exponents. Negative 32 raised to the negative 3/5. So the first thing I'm going to do is think about the previous section, 10.1, and what do I do when I have a negative exponent? And what we said in that section is we take a reciprocal. So this would be negative 32 raised to the positive 3/5. By pushing that down into the denominator, it changes the sign of the exponent from negative to positive. And then following what I did on the two examples above, I would take this one and I would make it 1/5 and break that 3 off to the side. So numerator, pull off as a regular power, denominator, leave it there. And then start thinking about what does that mean to have a 1/5. And what we're saying up here is that means you would take a 5th root. So I would take a 5th root of negative 32, and that power would just stay on the outside. And then to finish it off, I would think about what is the 5th root of negative 32. So the question there is, what to the 5th power would be negative 32? And if you think about that, just try it. 2 to the 5th would be 32. So if I made it negative 2 to the 5th, I'd get negative 32. So this should be, for the 5th root of negative 32, the number negative 2. And then I still have that exponent of 3. So 1 over negative 2 to the 3rd. Negative 2 times 2 is 4, times another negative 2 would make that negative 8. And then finally, I wouldn't like the negative in the denominator, so I would just pull that out front and say that my answer is negative 1/8. Alright, moving on to the next page, we just have a summary of what we saw in those last few examples. So let's go ahead and look at how we deal with a rational exponent. For the counting numbers m and n, where n does not equal 1 and b is any real number for which b to 1 over n is a real number, if you have b to the m over n, then you can break off the numerator as its own power and make that b to the 1 over n, and then have that all raised to the m. Alternatively, you could break the fraction off and make it its own power and have the whole number inside. It's usually easier to do it with this first method. And then the second thing that we saw in our last example is if you have a negative exponent for rational, you deal with that the same way you did with a negative that was an integer. You do a reciprocal to get rid of that negative exponent. And either power, b to the m over n or b to the negative m over n, is said to have a rational exponent. And just focusing on this b to the m over n form, I want to say one thing here that they didn't say in their box from the book, which is that that denominator tells you what kind of root to take. So you could rewrite this as the nth root of b, and then I would suggest in almost all cases it's better to have that m outside the root instead of in. So I would put that out here. You can put it in either. That's what they're really saying here when they put the m on the inside versus the outside, is it could be done in either order. But in most cases, you'd rather take your root of a smaller number and deal with the exponent afterwards. So even though this is all the stuff they had to say in the book there, I would say that this is really kind of the key thing that I like to think about when I'm converting a rational exponent into a root form. Alright, moving on to some other examples here. The other thing that we want to see is that all the exponent properties that we learned back in chapter 7 and then we saw again in section 10.1 apply to rational exponents just like they did to integer exponents. So if you have two things with the same base multiplied together, then you can combine those by adding their exponents. So this should become 3 to the 7/5 plus 3/5. And then those have a common denominator, so that's 3 to the 10/5 if I go ahead and add those up. And you might be tempted to make a fifth root out of this, but really what we should try and do first is simplify it. And 5 goes into 10 twice, so we can just make this 3 squared, and 3 squared is 9. So if we started taking roots right away on this, this would be a very messy problem. But if we use our exponent rules and we combine by adding our exponents, we end up getting an integer and can finish it off quickly. Alright, let's practice this a little bit more in the context of functions. We have an exponential function here. G of x is equal to 4 times 27 raised to the x power. And if we have a function, you should be allowed to plug any real number into that function, and that should include fractions and negative numbers. So when they ask us for g of negative 2/3, we're going to do what we've always done for functions, just substitute that negative 2/3 in for the x here, which I already did, and then in for the x on the other side where the function rule is. So that would be 4 times 27 raised to the x, but x is negative 2/3. So now I just want to simplify that. The first thing I would do is get rid of this negative exponent by moving the 27 to the 2/3 down to the denominator, and by pushing that down, the exponent changed from negative to positive. And then the next step that I would take is start trying to break that rational exponent apart. The 3 in the denominator tells me what kind of root to take. So that would be a cube root of 27. And so I've dealt with the 27 and the 3, but not the 2. So the 2 I'm going to break off to the side and just leave that as an exponent. And now I just do a couple steps to finish this off. So the cube root of 27 is 3, because 3 raised to the third is 27. I still have that 2 there, and then one more step, 3 squared is 9. So this is really a lot like the problems we were doing on the previous page, just trying to simplify a rational exponent. Just a couple things to note. The 4 out front has its own exponent of 1, and so when I got rid of this negative and pushed it down to the denominator, the 4 stayed up top because that exponent, the negative exponent, did not apply to the 4, only to the 27. And then secondly, once I get it to this point, the denominator is the type of root, the numerator stays as a regular exponent or power. Alright, let's try a couple more. So b to the 2/7 times b to the negative 6/7. There's a couple different ways to approach this. I could try and get rid of the negative exponent first, or because these have the same base, I could combine exponents through addition. I think I'll start with that second option. So I'll take b to the 2/7 and then plus the exponent from the other one, which would be plus negative 6/7. So I have b to the common denominator 7, and I have 2 minus 6 for the numerator. So that would be b raised to the 2 minus 6 is negative 4/7. And that is almost done, but I don't want to leave my answer with a negative exponent, so I would do a reciprocal and say this is 1 over b to the positive 4/7 in the denominator. Now I could split that up and make it a 7th root of b, all raised to the 4th power, but I'm not going to do that with a variable unless I see it an option to simplify it. And when your numerator is smaller than your denominator, writing that as a root is not going to allow you to simplify it unless you're dealing with a number, because then if you can write that number as a root, you might be able to simplify that. But with a variable, Once you get it to that point, you'd want to just stop. But you do need to get rid of that negative exponent like I did in the last step. Alright, one more, and it's just a little bit messier. We've got two different bases here, and so we're going to want to combine both of those. We also have fraction exponents and negative exponents, so we're just going to have to deal with all of that as we go through. So I would try and work with the like bases. So I would take these and combine them by adding exponents. So negative 4/3 plus negative 2/3 would be the exponent on the b's. And then I would want to do the same thing for the c's. My first exponent of 1/2 plus this negative exponent, negative 3/2. And then I'm just going to want to do the fraction work to simplify those and see where this goes. The first one, both numerators are negative, so they add together. That'd be negative 6 when I take the negative 4 plus the negative 2 over 3. And then for the c, I have 1 minus 3, which would be negative 2 over 2 for that one. And then fortunately, both of these denominators go into the numerator evenly. So that would be b raised to the negative 2 when 3 goes into the 6 twice. And here the 2's would cancel, and I'm left with c to the negative 1. And I've basically combined my b's and c's. I've gotten rid of my fractional exponents. The only problem that's still remaining is that I have negative exponents. But just like we did here, if the exponent's negative, we can simplify that by pushing those factors down into the denominator. So this becomes 1 over b squared and c to the first, or just c. And the 1 is important. If everything from your numerator is getting pushed down into the denominator, you still have to leave a 1 up there as a placeholder in the numerator. Alright, so that one was a pretty messy start, but because we had common denominators, we were able to combine those exponents quickly, and then luckily this went in evenly, so we were able to get rid of the rationals. Then it was just a matter of going back to the previous section and knowing how to deal with those negative exponents. Alright, I have one final example to finish off section 10.2, and this one is going to deal with some data and looking at the graphing calculator as well. So let's go ahead and read it and jump in. The numbers of countries that have participated in the Winter Olympics are shown in the table for various years. Let n be the number of countries participating in the Winter Olympics at t years since 1900. The situation can be described by the linear function n equals 0.815t minus 9.41, the quadratic function n equals 0.0087t squared minus 0.32t plus 19.95, and the exponential function n equals 10.1 times 1.02 to the t. So at the moment they're not telling us how they got those functions. We're going to look at that together later. I'll give you a little bit of insight into it right now. But first, they gave us years 1924 through 2006. But if we look back up here, where's our definition of t? It's t years since 1900. So I want to convert all of those values over to t. So I'm going to make a new column here for t, and I'm going to just take each of these years and subtract away 1900. So 1924 minus 1900 would be 24, 1948 minus that would be 48, and so on for 68, 88. And the last one, a little messier, but if you do 2006 minus 1900, you get 106. So those are our inputs, and these are our outputs. And then we have these three different models, and they want us to think about which one is the best. So we're going to use a graphing calculator to draw the graphs of all three models and the scattergram of the data together. So let's go ahead and enter this data into the calculator. So this will be a lot like we've done in previous sections. So let me just remind you how to get there. You want to hit the Stat key and then go into the Edit menu and enter all of your inputs into L1. So I'll do that. Once you have all of those into L1, and just make a note of that right here. So these would go into L1, and then I'd want to put the outputs into L2. So I'll just arrow over and enter those in as well. And then they want me to do a scattergram of the data. So I'm going to do that. Let me just make a quick mention here though of these other functions that they listed. If you think about how did they get this linear function, then if we went to stat calc, they're using the linear regression function that we were using back in chapter 5 and we'll continue to use. And then the quadratic function, we didn't talk about that. That's one of the chapters we skipped over. But if you're curious, how did they get that? They choose number 5, quadratic regression, L1, L2, and it gives them these coefficient numbers. That's not something you have to worry about, but that's how they got this. And then exponential regression we will be doing soon. And that one, you just have to arrow down a little bit. It's past our initial screen. But down there, number 0 actually is exponential regression. With this data, we'll give those two numbers. This is a little bit ahead, but I'm going to go ahead and do that. So exponential regression L1, comma L2. And we'll see that they're saying, okay, the format is a times b raised to the x, where a is 10.108897111. Well, if we rounded that to one decimal, it would be 10.1. And then our base, 1.0200618663. If we rounded that to two decimals, that would be 1.02. So they're not asking you to do that yet, but that's just a little insight into where they got those equations. They just used regression like we did back in chapter 5. It's just there's different kinds. Alright, so getting back to doing this scattergram right here, we want to set up our window. I would think for the X window, I would go ahead and use, I guess, the T window, but on the calculator it'll be X and Y. I need to go from 24 to 106, and they started talking about 1900, so I think I'll use a window there that goes from 0 up to, let's go 120. It's just good to give yourself a little room before your first data value and a little room after your last one. And then for the Y values, we have a minimum of 16 and a maximum of 85. I'll just go from 0 to 100 there for that window. So let's go ahead and set that up. I would press the window key, and for my X I'm going to go from 0 to 120. It seems like a decent scale there would be to go in tens. Scale's not that important on the graphing calculator. For the Y values, 0 to 100. We could go in fives, but 10 makes more sense to me, so I'll just go ahead and do that. And then I want to see what the scatter diagram looks like. Let me look at my y equals menu. I have a couple old equations in there, so I'll clear those out. And my plot is not highlighted, which means it's not set up to graph, so I'm going to highlight that plot 1, turn that plot on. It should already be set up to do a scatter for L1, L2, but I'm just going to double check by going into stat plot. So second stat plot, plot is on. It's a scatter for L1 and L2, and it's going to draw squares. So that seems perfect. So I'll hit the graph key, and there's the scatter diagram. So one of the things I'd like you to see in the scatter is it really seems like it's curving a little bit. And when you're dealing with a curved function, a line isn't necessarily the best choice. So let's go ahead and look at the 3 different choices they gave us, and we'll see how all of those fit. So let me enter those in by going to the y equals menu. The first one is linear, 0.815 times the input variable, which we always use the x for that, minus 9.41. I'll go ahead and hit graph, and we'll see that one. That's a reasonable fit for the data, but our argument in this chapter is going to be that because this looks like it's bending, if we had a graph that bent, we could probably do a better job getting close to all those values. So one bending shape is a U-shaped graph called a parabola, which comes from these quadratic functions. Again, we skipped that chapter, so don't worry too much about being an expert on this, but we do want to be able to type it in and see it. So 0.0087 times the input variable squared, and then minus 0.32 times the input variable again, and plus 19.95. So let me draw that graph. And I think if you just look at that, that graph seems to have come closer to pretty much every point in our scatter plot, except for maybe that one is right in between the line and this parabola, this bent curve, but that seems like a much better fit than the line. So hopefully you can see there that there is an advantage to learning some new types of modeling, because you can reduce the amount of error that you're getting. And then finally they gave us this exponential model right here, 10.1 times 1.02 to the t. So I'm going to go ahead and enter that one in as my third function. So I see that again, 10.1 times 1.02 raised to the input variable, which would be our x. And when I hit graph, it'll draw that one in. Hit that one, hit that one, hit that one, hit that one, hit that one. That definitely to me seems like the best fit so far. though it does blend in pretty good with the parabola. So we've got three different models. They're all decent, but the last two, the quadratic one and the exponential one, because they curve, did a better job for this curved data set. So which function likely describes the situation best for the years before 1916? What they're trying to get at here is just the idea of which of these is the best fit. One of the ways can be like which one came closest to the data. That's good enough. But another method we could use is think about, well, what if we were to kind of extrapolate a little bit before our 24 or after our 106, which one might do the best? And if you look at the linear one, by the time you get to 1916, it seems to be really low and perhaps even dipping down into a negative number of countries, which doesn't make sense. The quadratic one, because of its U shape, starts to turn around and go up. I can show you that a little better by taking the window and moving it to the left some. So I'm going to just show you some of the left side, some of the stuff from the 1800s, if you will. Negatives representing before the year 1900. So there's my linear model. There's the U-shaped one. You can see that bend to it now. And then here comes our exponential one. So when you think about before 1916, remember that I did 10, so this would be 1910, 1920. Around 1916, it looks like the linear one's going negative, so that doesn't make sense. Before 1916, the U-shaped one is saying that the number of countries was dropping, kind of reached a low and then went back up. But the Winter Olympics is kind of a newer thing, so I don't think back in the 1800s it was super popular and then dropped in popularity and then rebounded. So this exponential one that shows a steady curving growth probably makes the most sense for this one. So when they talk about which one is the best, I'm going to kind of do this by process of elimination, not linear, because it produces negative outputs. A negative output isn't necessarily something that can't happen in a function, but here our output is the number of countries, so that can't be negative. And then not the quadratic one, because it shows that it was declining before 1916. It shows that bend. So I'm kind of running out of room here, but we've eliminated those two, and so I would go with exponential. And I would say that's the best because it shows a steady curving increase. And I like the fact that it's curving because the data from the scatter plot looked like it was curving too. And so I'm going to do my best job of modeling if I take data that looks like it's curving and model it with something that's curving. So they're asking us to rule these out or to pick the best one. And they want us to base that off of like the flaws that happened before 1916. But I think just this idea that this one is the best fit is a good enough motivation to pick it. Alright, so we're going to pick the exponential as being the best one, and now we're going to use that to do some estimating. So use the exponential model to predict the number of countries that will participate in the 2014 Winter Olympics. So our function is supposed to model that. We're going to use the exponential model. So we're going to use n equals 10.1 times 1.02 raised to the t. For 2014, you would subtract the 1900 to figure out what your value of t is, and you'd get 114. So putting that together, the number of countries should be 10.1 times 1.02 raised to the 14th power. And I can do that on the calculator. Let me go ahead and exit out of this screen and clear that off. So we have 10.1 times 1.02 raised to the 14th power. And that ends up being 13.32, 13.33 I guess because of the 6. But really we should probably round that to the nearest whole number. And what do we get there? Something seems to have gone wrong. Alright, let me give myself a quick chance. Oh, I see what it is. I put in 14, but we said that was supposed to be 114. So okay, I fixed that to 114. Let's try that again. 10.1 times 1.02 raised to the 114th power would give something that makes more sense here. Approximately 96.55, or rounding it to the nearest whole number, about 97 countries. Alright, so I'm a little embarrassed. I made that mistake. I made it on camera. It's going to be there for all time. Or I could redo the video, right? I think I'm going to leave it here, and I just want you to see why. I want you to see how I caught my mistake there. Pretty easy mistake to accidentally put 14 instead of 114. But when I got an answer of 13, it just didn't make sense to me because I was thinking about a scatter plot that's curving upward like this, going from 16 countries to 28 to 37 to 57 to 85, and the model should say it's going to keep going up. So when I got an answer of 13.33, that just didn't make sense to me, so it caused me to stop and to look for a mistake, and then I found it and I was able to correct it. So I would encourage you to always be thinking about the size of an answer you're getting, and does it make sense with the data and with the kind of application that you're doing, and if it doesn't, use that as an opportunity to go back and fix it, to look for the mistake and then hopefully to fix it. Alright, let's finish this off with part D. Use the exponential model and the intersect to estimate when 42 countries participated in the Winter Olympics. So let's see, we had 37 countries in 1968, 57 countries in 88, so you'd expect somewhere in between there we would have hit that number, 42 countries. If we were trying to solve that, since 42 is the number of countries, that would get plugged in for the end spot, and we would do 42 equals 10.1 times 1.02 raised to the t. And if we started trying to do the algebra on this, it turns out we're going to get stuck because we don't know how to solve for an exponent that is a variable. We don't yet. We will later, but we don't know how to do that right now. So one of the things we learned in the past is that if you have some functions or an equation and you want to solve it, you can let the left side be one function, the right side be another, and then you can graph the two of them and use the intersect feature on the calculator to find where the solution would be. So I believe that I already put this exponential function in as y3. What I'm going to do is take the left side and put that in as y4, and then I'm going to try and find the intersection between those two graphs. So I'm going to go ahead and go back to the graphing calculator and hit the y equals key, and I already have graph 3 is the exponential. I'm going to go down and make graph 4 the number 42, and I'm going to turn off all the other stuff here. So I'm going to turn off plot 1, I'm going to highlight the equal sign, press enter, that turns off equation 1. Again, highlight the equal sign, press enter, that turns off that one. So the only two that have the highlighted equal sign are y3 and y4, so if I hit graph, those are the only two I'm going to see. So here's the exponential function drawing in, and then it's going to draw y equals 42, and where they hit, that should be when my exponential function is equal to 42. So I can kind of estimate that, 10, 20, 30, 40, 50, 60, 70. It looks like maybe in between 70 and 80 somewhere. But I can use the calc menu and intersect to figure that out more precisely. So is this my first curve, the exponential? Yes. Is this line my second curve? Yes. And then for my guess, the intersection looks like it's right around there, so around 72. I'll press enter, it'll zoom in on that. 71.966925 is their estimate. It's saying x, but I know my input variable is t, so t is around 71.966925, and then rounding that to the nearest year, that'd be approximately 72. And then since that's the number of years since 1900, I would say 1900 plus 72 and get 1972 for the year. So I would estimate that in 1972 that would be the year where we had 42 countries participating in the Winter Olympics. Alright, there's a lot to that one. Rewatch it as much as you may need to get down the different things that we were learning there, and we will practice these features on some future examples as well. Don't worry too much about the quadratic models. That's something from a chapter we skipped, so we'll just do quick mentions on that. But we want to get used to this idea that an exponential model can be used when you have data that forms a curving scatter plot like we did in this one. And I think that is pretty much it. So that finishes off section 10.2.